Hello everyone and welcome back. As you saw from the title, today's lecture is very important because we will be discussing Newton's first law. However, before I actually present Newton's first law, there's a few things we need to discuss. For starters, the last time we did force diagrams, and a term I used was point of view, aka front view, top view, side view, but in physics, the actual term for this is called reference frame. Now, in physics, reference frame doesn't just mean what direction you're looking at your object from. It also refers to what else is in view around your object. And in physics, there are two very important types of reference frame. Let's talk about both of them. The first type is called an inertial reference frame, a point of view where all forces that cause a change in an object's velocity are accounted for. 99% of the time, this is the type of reference frame you are going to use and the type of reference frame that you want. This means that all the forces exerted on your object and any change in the object's velocity is accounted for any other object within the point of view. In other words, you can tell why an object changed velocity by looking at the situation. Let me show you an example of this. Here we have some hardworking people that have just placed about 100 shopping carts into the back of this tractor trailer. They've just about finished. The trailer is ready to go, but one thing they have not done yet is close the door. And you can see the results pretty clearly. Now, looking at the situation, you can tell why the shopping carts left the trailer. Here comes the manager. The shopping carts never actually moved. It was the tractor trailer that moved. The shopping carts, because they have wheels with surprisingly little friction here, they stayed still. They did not have an unbalanced force to change their velocity. The truck had an unbalanced force from friction to change its velocity, but the carts stayed where they were. Once the carts left the trailer, the only thing left was force from the earth, which then pulled them downward. So this is an inertial reference frame because you can tell why any change of velocity occurred. Now, the second type of reference frame is called a non-inertial reference frame, a point of view where an object's velocity changes as if by magic. In other words, the forces causing the change are not accounted for. This means that your target object is changing velocity, but considering your point of view, you cannot tell why it is changing velocity. Sounds like a strange statement, so let me show you an example. Here we have some marbles inside of a box. One's hanging from a string. Two of them just started rolling toward the center. Now they're rolling toward the side. Now the point is, you can't tell why these marbles are changing velocity. They're stationary, then they increase velocity, then they slow down to a stop, then they change direction, and there's really no way to tell why they are doing this. So there's nothing pushing on them. You don't see any incline from this point of view. You don't see, and there go, they're up the wall. So from this point of view, it looks like this is magic. It looks like they're possessed. This is a non-inertial reference frame. So, in order to demonstrate the change in velocity of an object due to forces exerted, we're going to use this cute simulation. This is going to be an inertial reference frame because you will be able to see all the forces that cause the object to change velocity. And our object is going to be this cart with frictionless wheels and is full of candy, so the object does have mass. Now, this is a tug of war scenario. We're going to have red team versus blue team. So red versus blue. And we're going to take two people from the blue team and two people from the red team. And I'm going to hit go and they're going to start to pull. So before I do any of these, a good thing to do mentally is to predict what is going to happen to the cart. As you can see with the arrows, it shows force to the left and force to the right. And it shows the sum of forces, also known as the net force. Let's hit go. Well, as you can see, the cart is not going anywhere. The cart is not going anywhere because the forces applied are equal and they cancel, which means the cart does not change velocity. So Let's return everyone, make one small change. I'm going to add one more person to the blue team here. The card is at rest. I'm now going to hit go. Let's see what happens. Card starts at rest. Card is moving left, and the card is speeding up to the left, and the blue team is obviously going to win here. So I'm going to return. So that was probably easy to predict. Let's do one more scenario. I'm going to start the same contest again. Blue team obviously has the advantage. I'm going to pause it, and the red team, seeing that their team is in trouble, everyone runs out onto the field, and they start pulling to the right. Now, I'm going to hit go. This is paused right now. I'm going to hit go. So the very first question that I would like you to answer in your mind is, as soon as I hit go, what direction is that car going to be moving in? Ready? Did you see it? As you just saw, this cart is still currently moving to the left, even though the net force is to the right. The cart is still moving to the left, and that is going to be a big point with force diagrams. Since I have this situation paused, the force diagram does not tell you what direction the cart is moving. However, if you know what direction the cart is moving, the force diagram will tell you what is going to happen. So this cart is currently moving to the left. If I keep the forces the way they are, what is going to happen to the cart? Let's find out. The cart is moving left, it slows down, comes to a stop, is moving to the right, and it is speeding up. To demonstrate that again, let's take a bunch of guys off the red side and add to the blue. So I'm going to hit go. The cart is currently moving to the right. Slows down, comes to a stop right there. I'm going to pause it. Then it speeds up to the left and getting faster, 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 faster until they win. The net force will immediately begin to change the velocity of an object, but the object won't start going in the opposite direction right away. It has to slow down, come to a stop, and then start moving the opposite direction, and then it will start speeding up as long as those forces remain unbalanced. To give you one further demonstration of this, let's take a look at this situation that I have already paused. So to look at it, I have the cart, it's a little off center. I have the blue team on the left, which is producing a lot more force than the red team on the right, and the sum of the forces, which is the net forces to the left. I'm going to hit go. The question is, as soon as I hit go, what direction is this cart going to be moving in? Ready? Do you see it? So I hit go, and the cart is moving to the right. I did this to really get the point across that a force diagram does not tell you the velocity of the object right now. However, if you happen to know the velocity of the object, a force diagram will tell you what is going to happen to the object. Now that we know this card is going to the right, looking at our force diagram and the fact that net force is to the left, this cart is going to slow down, come to a stop, begin to move to the left, and then speed up. And now it's going to get faster, 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 faster. Wait. So I have one more situation to show you, and it is probably the most important one. For starters, let me put these two here. I have a speed meter on here, and just to show you, the speed meter keeps going up, 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 up until it hits to the end, and that is because the forces here are unbalanced. Now, I'm going to start this again and pause it right here. Then I'm going to put the same amount of force on the other side. And my question is this: when I hit go, what is going to happen to that cart? Is it going to speed up? It is already going to the right, remember. Is it going to speed up? Is it going to slow down? Is it not going to move? Let's find out. So if you see, the cart is still moving to the right, but if you notice, there's something else that's even more important that's going on. Let's back up and I'll show you again. So I have the forces unbalanced. All right, I'm going to pause it right here. So there's a little bit of speed. I'm going to even out these forces and now hit go and watch the cart carefully. What is happening to this velocity? The answer is nothing. The velocity is not changing. That is a very key point here. And that is actually one of the most important things you could understand in physics. I'm going to return. I should see you one more time. Put it back. So here's the deal. The force on the right is trying to increase the velocity, and the force on the left is trying to decrease the velocity. If they are balanced, then neither wins. Neither of those two things happen. This is not about making the cart go or making the cart stop. This is about changing the cart's velocity. The red team is trying to make the velocity go higher. The blue team is trying to make the velocity go lower, but if they are equal, the velocity does not change. In a sense, this is no different than if I start this competition right now. The velocity is 0. Since they're balanced, the velocity remains at 0. If, let's go a little bit, let's say the velocity is 2 meters a second. I hit go, the velocity stays at 2 meters a second. And that is, in a nutshell, is Newton's first law. So let's actually discuss the proper wording of that law. Okay, it's time for the big reveal. I'm going to present Newton's first law. Then we're going to discuss the law in detail. Because remember, if for Newton's laws, there's 3 levels of understanding. The first level is knowing the words. The second level is having an understanding of what the individual words mean. And the third level is actually being able to apply the law to physical situations. So let's present Newton's first law. If all forces exerted on an object are balanced, it will have a constant velocity. If they are not balanced, it will change velocity. That's it. This was shown very specifically with the candy cart tug of war. Specifically, that last situation when I had the cart moving and then had the forces balanced. If the forces are balanced, the velocity does not change. If an object is moving at 20 kilometers an hour in a straight line, it will continue to do so. If an object is moving at 0 meters a second and the forces are balanced, it will continue to stay at 0 meters a second. The velocity does not change, not if the forces are 0, but if the forces are balanced. That means if the forces are balanced, the net force is 0. So if all forces on an object are balanced, then the velocity of an object does not change. If they're not balanced, the velocity of the object will change. Now, forces we just discussed, but the most important word in here is the word velocity. Velocity by definition is speed and direction. This means that if the forces are balanced, neither speed nor direction will change. If that object is either speeding up, slowing down, or its direction is changing, that means you have a non-zero net force and the forces are not balanced. At the bottom here, just a note, first law is specifically in reference to an inertial reference frame, which I showed you earlier. It is very rare that you deal with a non-inertial reference frame in a first-year physics course. Just a little note, Newton's laws are so powerful that they come up in popular culture pretty often. This is not the way first law was originally written, and there's a reason for that. Newton's first law was actually published in 1687. That was over 300 years ago. And in that time, the way language is used and words are used has changed. Newton's first law, as it was originally written, is a great piece of physics history. However, for someone learning physics for the first time, this is a much more accurate representation for Newton's first law and how it will be applied in a physics course. Thank you for joining me, and I hope you have a good day. This is Mr. M signing off.